To use the water table recharge tool, determine appropriate parameters for your system, then click on the green Run button at the top of any WTR page to bring up the input form. Example values are provided as defaults. Enter the average representative values of each parameter for your field system. For this example, I enter arbitrary but reasonable values. It is important to enter values in the appropriate units, which are meters and days, for all inputs except net recharge, which is in millimeters per year, and is equal to annual precipitation minus annual runoff and evapotranspiration. 50 meters for length, 12 for surface elevation. The only use of this is for the model to indicate when the water table may be unreasonably high. 10 meters for head on the left. The water table can be higher on the right or the left. 8 meters for head on the right. 0.01 meters per day for hydraulic conductivity. 100 millimeters per year for net recharge. 4 significant figures in the results, and 1 to display results in decimal rather than scientific format. Then click Submit, and results appear below the input form. The net recharge is precipitation minus runoff minus evapotranspiration and is shown in millimeters per year and converted to meters per day. Next, flow to the left, top, and right boundaries is printed in cubic meters per day per meter of length into the drawing. That is, flow to or from each meter of land at the surface and each meter along the bank of the water body represented by the constant heads. Positive values represent flow to the right or down. Negative values represent flow to the left or up. If the net recharge is negative, it is shown in red to draw attention to it in case it is an input error. The volumetric budget balances, with the inflow at the surface being equal to the sum of outflow to the left and right water bodies. That is, 0.01369 is equal to 0.003245 plus 0.01044. For this analytical model, the sign of the flow rate indicates the direction of flow, with positive being to the right and down. The distance to the groundwater divide from the left boundary is displayed along with the head at that location. Graphs of the water table elevation and the flow rate are displayed with elevation of the water table in blue and flow rate in orange. On a computer, hovering the cursor over the line of the graph indicates the Y value at each X value. On a mobile device, lightly touching the curve provides the Y value, while dragging your finger on the graph shifts and resizes it. If the adjusted view is not useful, you can return to the original view by pushing Submit again. If I input unreasonable values, messages are provided to draw attention to input errors and the possibility that the results are unexpected or unreasonable. For example, a negative value for a head at a boundary represents a physical impossibility because it means the thickness of the aquifer at the boundary is less than 0, so no flow could occur. Thus, if I enter a -8 for the head on the right, rather than getting results, a message appears in red, indicating the head must be greater than 0. Results are not printed, and the graph shows 0 for every value of X. If I correct the error and press Submit, the results are displayed. If I enter a combination of values that results in the water table being higher than the land surface, in this case K equals 0.001 meters per day, a red message appears indicating how much higher, in this case about 4 meters. If the net recharge is quite small, say 1 millimeter per year, a divide will not develop. The results will explain that the divide is calculated outside the domain at a distance equal to what would be required to accumulate sufficient recharge to equal the inflow at the boundary. This is a logical result mathematically, but does not have physical significance. If I enter a combination of values that results in the water table being below the aquifer bottom, error messages are printed. In this case, I enter net recharge of minus 600 millimeters per year, so groundwater is discharging up through the surface at a rate so high that it cannot be supported given the input properties for the aquifer. Although the mathematics show balanced flow, the situation is not physically possible. The results are not valid because the assumptions made to develop the equations are broken. That is, uniform flow cannot occur at the surface given that nearly half the aquifer is dry at the values required to support the flow, and the flow cannot be viewed as approximately horizontal. As with all models, we have to employ our common sense when evaluating results. If I enter a value less than 1 for significant figures, a red message is printed, but the tool proceeds using a value of 3. If I enter a value greater than 20 for significant figures, a red message is printed, but the tool proceeds using 20. If I enter a value that is not 1 or 2 for notation, a red message is printed, but the tool proceeds using 1. I hope you enjoy using this interactive tool.